Welcome to chapter 7 of this paper. In this paper, we are going to cover trees, Eulerian graphs, Hamiltonian graphs, planar graphs and other concepts like coloring of a graph, matching of a graph, vertex covering and edge covering of a graph. In this module, we are going to cover special type of graphs called trees. A tree is a connected acyclic graph. First, we are going to show or we are going to give few equivalent statements of trees. For example, a graph in which any two vertices have a unique path between them, then it is a tree. A connected graph in which every edge is a bridge is a tree. A graph with n vertices, n minus 1 edges and acyclic is a tree, etc. Chapter 7 about graph properties. In this first module of this chapter, we are going to discuss about trees. Objectives of this module are properties of trees, spanning trees of a connected graph, minimal spanning trees. Definition of a tree: recall that a graph with no cycles is called as acyclic. An acyclic graph is called a forest. A forest having one component is called a tree, that is, tree is a connected acyclic graph. A tree T with only one vertex is called a trivial tree and is called a non-trivial tree otherwise. The following 6 non-isomorphic trees on 6 vertices. This is a tree with 6 vertices, and it is also, we observed that it is a path with 6 vertices, and it is another tree with 6 vertices. These two are non-isomorphic, that is easy to see. This second graph contains a vertex of degree 3, whereas first graph does not have a vertex of degree 3. And another graph, another tree with 6 vertices. All these are non-isomorphic trees with on 6 vertices. These are the only trees on 6 vertices which are not isomorphic. The table of number of non-isomorphic trees: number of vertices is 1, then number of non-isomorphic trees is only 1. With 2 vertices also there is only 1 tree. With 3 vertices also we have only 1 non-isomorphic tree. With 4 vertices we have 2 trees. Like that, with 9 vertices we have 47, with 16 vertices we have 19,360 non-isomorphic trees. Now, we will see equivalent statements for a tree. Let X be a simple graph and n vertices, then the following statements are equivalent. X is a tree, that is connected acyclic graph. There is a unique path between any two vertices of X. X is connected and has exactly n minus 1 edges. So, throughout this we are assuming that X is a simple graph on n vertices. X contains no cycles and has n minus 1 edges. X is minimally connected, that is, every edge is a bridge. First we are going to show 1 implies 2. One is X is a tree, and second one is there is a unique path between any two vertices of X. So, first we are going to show that if X is a tree, then there is a unique path between any two vertices of X. Let X be a tree, then X is connected and there is a path between any two vertices. So, there is always a path now, so it is connected because of connectedness. Suppose there exist two distinct paths between pair of vertices, say u comma v belongs to v of x, then the union of these two paths produces a cycle. That is a contradiction. It is because we are showing that there exists a unique path between any two vertices. Once we have a cycle, then there exist two distinct paths. So, 1 implies 2 is clear now. Now, 2 implies 1. Here what we have to show that if there exists a unique path between any two vertices, then we have to show that that is a tree. That is, we need to show that it is connected and acyclic. Since there exists a unique path between any two vertices, then automatically the graph is connected. So, only thing we have to show is that it has no cycles. On the contrary, assume that there is a cycle in the graph, then there exist at least two vertices on this cycle that have two distinct paths between them, hence a contradiction. Now we are going to show 2 implies 3. Let X be a connected graph with unique path between any two vertices. This is the second statement. Then clearly X is connected. We will show that X has n minus 1 edges, that we have to show, that is the statement of 3. We will show that X has n minus 1 edges by induction on n, that is n is the number of vertices. The result is clearly true if n equal to 1 or 2 or 3. So now assume that the result is true for all graphs containing less than k vertices, and let X be a graph with k vertices. Since there is a unique path between any two vertices, if you remove any edge E from the graph X, that is X minus E has k vertices but has two connected components, say x1 and x2, with vertices k1 greater than or equal to 1 and k2 greater than or equal to 1 respectively, with k1 plus k2 equal to k. Thus by induction x1 and x2 contain k1 minus 1 and k2 minus 1 edges respectively. Thus the number of edges in X is k1 minus 1 plus k2 minus 1 plus 1, that is equal to k minus 1. So we proved 2 implies 3. Now we are going to show 3 implies 4, that is if X is a graph with n vertices and no cycles and n minus 1 edges, then we have to show the fourth statement. Let X be a connected graph having exactly n minus 1 edges. We have to show that X has no cycles. On the contrary, assume that X has at least one cycle. Then if you delete any edge from the cycle, a new graph is still connected and hence it has at least n minus 1 edges. Thus we arrive at a contradiction. So in this, what we proved is, if X is connected and has exactly n minus 1 edges, then it does not have a cycle. Now we are going to show 4 implies 5, that is in this case suppose X has k components, we will show k equal to 1. Since X is acyclic graph, each component is acyclic, that is each component is a tree, hence we can use 1 implies if and only if 2 implies 3. X contains n minus k edges, thus k equal to 1 and therefore X is a tree. Hence there is a unique path between any two vertices in X. Here we will use 1 if and only if 2. Hence every edge is a bridge. Now we are going to show 5 implies 1. Let X be a minimally connected, then X is connected and there exists a unique path between any two vertices, that X is a tree. Here we will use 1 if and only if 2. Now we are going to show an important result called every non-trivial tree contains at least 2 vertices of degree 1. Let T be a tree on n vertices, let d1, d2 and so on dn be the degree sequence of T. Thus by using first theorem on graph theory, we have that summation I is equal to 1 to n, dA is equal to 2n minus 2. As we know that a tree has n minus 1 edges, so the number of edges, twice the number of edges is equal to sum of the degrees. So summation I is equal to 1 to n, dA is equal to 2 times n minus 2, 2n minus 2. Now let L be number of vertices of degree 1 in T, then the degree of other vertices is at least 2. So hence dn minus 2 is equal to all vertices of degree greater than 1, dA greater than 1, dA plus L. So which is greater than or equal to 2 into n minus L plus L. So therefore we are going to get L is greater than or equal to 2. So we showed that if a tree has at least 2 vertices, then it has at least 2 vertices of degree 1. Note that path graph have exactly 2 pendant vertices, whereas the star graph on n vertices has n minus 1 pendant vertices. These are 2 extreme graphs. Path graph has exactly 2 pendant vertices, whereas star graph has n minus 1 pendant vertices. Let X be a connected graph with degree sequence d1, d2 and so on dn. Then X is a tree if and only if summation I is equal to 1 to n, di is equal to 2n minus 2. So, this is an if and only if condition. This is a nice criterion that by using degree sequence it is possible to characterize whether given connected graph is a tree or not. Look at in the hypothesis we are assuming X is connected graph. So, X is tree if and only if sum of the degrees of all vertices is equal to 2 into n minus 1. So, the proof goes like this. If X is a tree, then using first term on graph theory, we see that summation I is equal to 1 to n, di is equal to 2n minus 2. It is because tree has n minus 1 edges. Conversely, suppose that summation I is equal to 1 to n, di is equal to 2n minus 2, then we have to show that T is a tree or X is a tree. We will prove the result by induction on n. If n is equal to 2, then d1 plus d2 is equal to 2, and since X is connected, one has d1 comma d2 greater than or equal to 1, thus d1 is equal to d2 equal to 1, hence we have X equal to k2, that is a tree. So, let us assume the result is true for all connected graphs on n is equal to k greater than or equal to 3 vertices. Now, consider the connected graph X on n equal to k plus 1 vertices with degree of the vertices as d1 is greater than or equal to d2 greater than or equal to dk greater than or equal to dk plus 1. Then by assumption summation I is equal to 1 to k plus 1 di is equal to 2 times k plus 1 minus 2, 2n minus 2, n is equal to k plus 1. So, we have 2k plus 1 minus 2. As di is greater than or equal to di plus 1 for each I 1, 2, 3 and so on k, one concludes that d1 is greater than or equal to 2 and dk and dk plus 1 has to be 1. It is because every tree has at least 2 vertices of degree 1, 2 pendant vertices. So, let u be a vertex with degree of u equal to dk plus 1. As u is pendant vertex, it is adjacent to unique vertex A v with the degree of v is equal to dl. Note that dl is greater than or equal to 2 as graph is connected and k is equal to 3. So, now we consider the graph y is equal to x minus u, means deleted graph, deleting the vertex u, vertex deleted graph. This graph is connected and has on k vertices with degree of its vertices being d1 up to dl minus 1, dl minus 1, dl plus 1 and so on up to dk. Also note that d1 plus d2 and so on plus dl minus 1 plus dl minus 1 plus dl plus 1 and so on dk is equal to summation I is equal to 1 to k plus 1 di minus 1 minus dk plus 1, which is equal to 2 times k plus 1 minus 2, that is 2k minus 2. Hence, the induction hypothesis, the graph y represents a tree, thus the graph x indeed a tree on k plus 1 vertices, hence the proof. Now, we are going to show another properties of tree. Every tree is a bipartite graph. So, proof is very simple. We know that a graph is bipartite if and only if the length of every cycle is even. As tree has no cycles, so every cycle is of length 0, that means every cycle is of even length. So, the statement is true. So we done. So, in this way it is very easy to show. Now, we will see alternative proof. Let T equal to V comma E be a tree on n vertices. Let V belongs to V. Now, we construct two sets V1 comma V2 such that V is equal to V1 union V2 and every edge in T contains one end vertex in V1 and one in V2, that we have to show. So, we will build these sets recursively. Initially set V1 is equal to V2 equal to empty in the first step, but in the first step what we will take, V1 is equal to V and V2 equal to empty. In the second step V1 is equal to V as it is and V2 we will take all neighbors of V. In the third step V1 is equal to V union all vertices which are in the neighbors of in V2, that is V2 is actually neighborhood of V. So, we are taking all the neighbors of the vertices which are in V2 and V2 equal to neighborhood of V as it is. We continue this process till all vertices are traversed. Note that this process will end in at most n steps. It is because it is a tree with n vertices. Now, we will show that every tree has either one or two centers. So, statement of the theorem is every tree has either one or two centers. The result is clearly true if T has at most 3 vertices. So, consider a tree with 4 or more vertices. Then by corollary 1, that is in the previous result, T has at least 2 pendant vertices. This we showed that every tree has at least 2 pendant vertices. They are not centers. Since this tree has at least 4 vertices, so pendant vertices are no longer centers. Let T dash be a graph obtained by D by deleting all pendant vertices of T, then T dash is still a tree and both T and T dash have same centers. That is easy to see. Thus, we can use the induction argument to prove the required result. Since now T dash has less number of vertices than T, so it can be done. We saw various properties of trees. We showed that every tree with 2 or more vertices has at least 2 pendant vertices. We also showed that every tree is a bipartite graph. And finally, we showed that every tree has 1 or 2 centers. Now, we are going to introduce a concept called spanning tree of a connected graph. Now, we will define the concept spanning tree of a connected graph. A spanning tree of a connected graph is a spanning subgraph which is also a tree. Every finite graph is connected graph if and only if it has a spanning tree. So, it is a nice criterion, a graph is connected if and only if it has a spanning tree. So, the proof goes like this: if a graph contains a spanning tree, then clearly it is connected. So, one direction is easy to see. Since every tree is connected, if a graph itself contains a spanning tree, then it is clearly connected. So, it is sufficient to prove that every finite connected graph has a spanning tree. We will prove this by induction on the number of cycles, say C, in the graph. If a graph has no cycles and it is connected, so by definition graph is a tree and hence it is its own spanning tree. This makes a good base step for the proof. Now, by induction on the number of cycles of the graph, that every connected graph has a spanning tree. So, now let the result is true for every graph X that contains fewer than C greater than 0 cycles. Now, consider a graph X that has C cycles. Choose a cycle of X and choose an edge, say E of that cycle. Then if you delete edge E from the graph X, that is X minus E, edge deleted subgraph of X, that is X minus E, has fewer than C cycles, hence by induction hypothesis the resulting graph has a spanning tree. So, once the resulting graph has x minus e has a spanning tree, but then the spanning tree is also spanning tree for the graph x. Therefore, by principle of mathematical induction, every finite connected graph has a spanning tree. So, with this we proved this proof, that is, a graph is connected if and only if it has a spanning tree. Now, because of this, we are going to define circuit rank of a connected graph x. Circuit rank of x is defined as, let x be a connected graph and n vertices and m edges. As a spanning tree has to contain n minus 1 edges, so we have to remove, we will remove n minus 1 from m. So, the remaining edges, that is m minus 1 n plus 1 edges, which that is called the circuit rank of x, that is excess of edges in x than n minus 1, that is called circuit rank of x. That is, circuit rank of x is the number of edges that must be removed from the graph x to obtain the spanning tree of x. Let T be a spanning tree of the graph x, then in edge of x that is also is in T is called branch of x. So, we are taking T is at spanning tree of a graph x, and if the edge of x is also is in T, then it is called branch of x. Actually, every edge of x need not be in T, it is because T has exactly n minus 1 edges, but graph may have more than n minus 1 edges. The edge of x that is not in T is called chord or a tie or a link of x with respect to that spanning tree. It is clear that we can spanning tree, it is an edge is a whether a branch or a link, it depends upon the given spanning tree. The set of all chords of x is called chord set or tie set or cotree. Note that number of elements in the tie set is a circuit rank of x. The concept of spanning tree, circuits, cut sets etc. are related to, are closely related. To understand this relationship, we first note that the branches and chords are defined with respect to a given spanning tree, that is, an edge which is branch with respect to one spanning tree may be chord with respect to another spanning tree. So, let x be a given graph with a spanning tree T, then we have the following definitions. The fundamental circuit, any circuit of x that can be obtained by adding a chord to T is called a fundamental circuit of x. The set of m minus n plus 1 circuits obtained in this way is called fundamental system of circuits related to T. Since a fundamental circuit contains only one chord of T, it is referred to as fundamental circuit corresponding to the chord. Fundamental cut set, since a removal of any branch from T decomposes T into two trees, it follows that corresponding to every branch of T there is a cut set. The set of all n minus 1 cut sets obtained in this way is called fundamental system of cut sets relative to T. Since a fundamental cut set contains only one branch of T, it is referred to as fundamental cut set corresponding to that branch. Every chord of T defines a unique fundamental circuit and every branch of T defines unique fundamental cut set. The ring sum of these two cut sets in a graph is a third cut set or an edge disjoint union of cut sets. Now, we are going to define a weighted graph. A graph is said to be weighted graph, in particular edge weighted graph, if each of its edges is assigned a number called a weight. That means a graph is said to be weighted graph, of course with respect to edge weighted graph, if each of its edges are given with certain number called weight. Let x be a weighted graph, then spanning tree with minimum weight That means we are now looking for a connected graph and which is also weighted graph. Then we look at different spanning trees, and then we will add all the weights in that spanning tree. Then that is called total weight. We will take the total weight. So out of all the spanning trees, the minimum total weight, it is called a minimal spanning tree of the graph X. That is, the minimum spanning tree, say T, of undirected connected graph is a spanning tree with total weight, the sum of the weights of all edges in T being as low as possible. Now we will see some algorithms which are going to give minimal spanning trees. First algorithm in this direction is a Kruskal's algorithm. This algorithm finds a minimum spanning tree of a weighted graph. So the algorithm goes like this. This algorithm gives a minimal spanning tree of a weighted graph. So what is the input we have to have? First, the input is a connected graph with non-negative weights assigned to each edge. This is important. We are giving non-negative weights. And output is minimal spanning tree of X, just not a spanning tree, minimal spanning tree. So what is the procedure? The procedure goes like this. Select any edge of minimum value which is not a loop. This is the first edge of T. We are constructing T, the spanning tree, minimal spanning tree. If there is more than one edge of the minimal value, then arbitrarily we can choose one of them. So this step itself says that minimal spanning trees are not unique. Now from the remaining edge of X, select an edge which has a minimal weight and that does not form a circuit with the edges which are already included in T. So it is because we are constructing tree, so tree is a acyclic graph. Now continue step 2 until T contains n minus 1 edges, where n is the number of vertices of X. So we will repeat. First we will select an edge of minimum value which is not in the loop, that is called first edge of T. That can be any edge we can select, but the main thing is that edge has a minimal value. Once in the remaining edges, again we select the edges with the minimum weight, but which are not in T and which also does not form a cycle with the edges in T. Now we will continue this step until T contains n minus 1 edges. In Kruskal's algorithm, we have listed all the edge weights in increasing order. The following algorithm does not require listing of edge weights. We are going to give next algorithm. In that algorithm does not require listing of edge weights. So this algorithm is named as Prim's algorithm. This algorithm also finds minimal spanning tree in a weighted graph. Input for this algorithm is a connected graph X with non-negative weights assigned to each edge. Output is minimal spanning tree for X. The procedure is, we will choose a vertex of arbitrarily, say V1, then we choose another vertex, say V2, in the neighborhood of V1, such that the weight of the edge V1, V2 is the least among all the edges that are incident with V1. Now we look at the vertices which are adjacent to either V1 or V2. Again, among all the vertices in the neighborhood of V1 union neighborhood of V2, we choose a vertex, say V3, whose edge weight is the least. Now the newly constructed graph contains 3 vertices V1, V2, V3 and 2 edges. One of the edges is V1, V2, other edge is either V1, V3 or V2, V3. Now we choose the vertex V4 which is adjacent to V1 or V2 or V3 such that the new edge has a minimum weight and this edge does not form a cycle with the existing edges. we continue the above process till all the vertices are traversed or n-1 edges are added to the spanning tree. Observe that at any intermediate step of Kruskal's algorithm produces a forest, whereas Prim's algorithm produces a tree. We showed that a graph is connected if and only if it has a spanning tree. We defined the concept of weighted graph and minimal spanning tree of a connected weighted graph. We given two algorithms named Prim's algorithm and Kruskal algorithm. They are going to provide minimal spanning trees of a connected weighted graph. With this we end this module.